In the last video, we asked the question, what will be the temperature created by some current in a trace on a PCB? Now we are asking, how long will it take to get to the final temperature when we heat with some input power or equivalently with some current. To calculate this manually is almost impossible. Of course, we can simulate that numerically. But let me first make some comments. If you look the curves, curve number 1 is voltage as function of time. If we have an RC circuit and we instantaneously switch on current at time 0, the current will increase and then come to a steady state, and the typical time needed to increase by a substantial amount is called the time constant. In the electric circuit, the time constant is resistance times capacity, and if you look at the units, ohm times farad, volt over ampere, amp second, which is coulomb, divided by volt gives time. In the thermal analogy, we have to replace the electric resistance by a thermal resistance of the board to the ambient, and the electric capacity by the thermal capacity. This product is also some time. Thermal resistance, Kelvin over watt, and thermal capacity, a joule per Kelvin. A joule is a watt second, and the result of the product is seconds. Okay, what is the thermal resistance of the board? That's simple enough. It's 1 over the heat transfer coefficient we already learned yesterday, around 10, times the surface area. And what is the thermal capacity? This is mass of our product times specific heat capacity. Or if we have a mix of material, the portion material 1 in mass and specific heat capacity plus material 2, mass of material 2 times specific heat capacity number 2 of material 2. In a very crude estimate, we could write down this equation or this estimate. 1 over 10, heat transfer coefficient of 10, times surface area of the board is length times width multiplied by 2 because we have a front side and a back side. And the mass, that's an estimate, say 100 gram, and the specific heat capacity estimated 1500 or 2000. That's a mix of copper and FR4. I don't know this in advance. The software will calculate it. By numbers, we get 3 Kelvin by watt, and this product is 150, and the total product is more or less 150 seconds. 450, sorry, this is a typo. Let us look at the time constant. It is said that you need about 5 time constants to reach the final equilibrium. That's in the electric case and the thermal case. Let me go to TRM and calculate that in more detail. I created a copy of our model from the last video, and we are asking for the time. There's no need to change the settings, except in this table it would be nice to have numerical thermal couples. For example, a thermal couple in the center and a thermal couple at the end of the trace. I can create this graphically, just sketch it. It doesn't matter where the perfect spot is, and draw a circle here and draw a circle there. And the first circle is called thermal couple center. The second circle is called thermal couple right. And the third one, thermal couple left. And of course they should be in the same plane of calculation as the trace, which means they should have a 1 here and a 1 there. The materials are ignored, the power is ignored when we have the keyword TC. Now we are ready to run it. Run number 2, transient, and I have to click the keyword transient. Starting the calculation will now calculate the true value of the heat capacity and the thermal resistance. And the product is 116 seconds, not 450. Okay. We have to give some time steps. First of all, the final time. And it said that 5 times the time constants leads to equilibrium. Let's take 1000 seconds for the final time and some time for the first time step, say 3 seconds. This is a preview. It's not very precise, but it is showing us the density of the computational points with respect to time. We have 19 time steps and we just run it. I'm pausing because this will take maybe 2 or 3 minutes to calculate, and I'm back soon. By now we created some time steps, and this is the current situation. The last time step at about 260 seconds. It's almost in steady state. This is the convergence for each time step, and my setting was 1000 seconds as final time. Unnecessarily long, but you don't know in advance how long it will take. So let's be patient. Now we are done, and we are watching the result. The steady state temperature is 40 degrees, as expected, but we can look at the transient heating curve, which is this one, time, temperature, starting from 20 degree ambient. This, the black line is the maximum temperature, which is close to the center. We just estimated the thermal couple in the center, and this is the temperature close to the left and the right end. What is interesting with this type of calculation, of course, it could have been that the current was, say, 50 amp, and we want to know how long does it take until the temperature at 50 amps is reaching a certain threshold, and many things more. For example, we could have a look at in the TRM manual. You may also add an Excel file describing on and off states or modulation of the input value as a function of time. And the result is a profile like this. Thank you for watching and stay tuned. Goodbye.